So our next presenter is Shri MV Peereswara Rao. He's a senior scientist of rank Scientist G, which is considered as a very high post at UR Rao Satellite Center in ISRO, and has a major contributions to many successful Indian satellite programs, including Chandrayaan, Mangalyaan, and Gaganyaan, Mars, Moon, and human spaceflight missions, respectively. Having obtained his master's on asymptotically correct methods for honeycomb sandwich panels from NMCAD Lab,
is the EXE file.
also
Yeah, first we have to install that. Once that
is also you can continue. So our next presenter is Peereswara Rao, and he's a former NM cadet. He's also currently pursuing his PhD at our lab and is working on dimensionally reducible macro/micro beam plate models using VAM. Thank you.
And also probably introduce
So he'll be joined by Mr. Jebin Thomas. He's a former research associate at NMCAD Lab, since his master's from NIT Trichy, and will be speaking on VAM and its application in dimensionally reduced models. He has also worked on bladed rings for aircraft engines as well as airship design and development. Please welcome.
Good afternoon, sir. Good afternoon, ma'am. And very good afternoon to all my senior as well as junior colleagues of NMCAD. So I'll be presenting about variational asymptotic methods and
Dirishwara, there's a camera there, so maybe you can select the live audience.
the topic of today's discussion, which I'll be talking about, is the variational asymptotic method and its application to reducible. So for the last 3 days, many of us have been heard about the variational asymptotic method, especially for the people who are not from the NMCAD. So this will give an overview of VAM and its application. So though it is best for the reducible model for any function, which can be having small parameters. So this presentation is divided three. Is the work for the VAM and how it is applied in the form of a flowchart. I will also be discussing each and every step of the flowchart, how it is applicable for the beam and how it is going to be applicable for the plate. And the second part will be the application of VAM for the sandwich-like structures, which will form as a plate-like structure. And the third part will be in the form for the beam-like structure, which will be dealt by the Jebin Thomas. So especially in all our structures, which we see the assembly of structure, where we'll be having the primary load bearing, secondary load bearing, and tertiary load bearing structures. These are assembly of mainly three type of structural elements, which can be divided as the components are the structural components where all the dimensions are comparable, are the structural elements where one of its dimension is less when we compare to the other two dimensions, and finally the structural elements where two dimensions are very less when we compare to the other dimensions. So these comes under the reducible structures. For the industries which we use, we generally use all the three types of structural elements. And the existing 3D elasticity solutions cannot be used because of intricacy in the geometry, material properties, loads, and boundary conditions. Hence, in the industry, we use numerical methods, and the versatile numerical methods which is used as on today is the finite element method. But these, when we use for the entire structure to do the analysis by using finite element, to obtain the accurate solution, we have to use the 3D finite element. But using the 3D finite elements is very costly in terms of generating the model. Even if you generate the model, the hygiene of the model to meet the quality parameters of the finite elements and the turnaround time to obtain the results is also very large. And moreover, the results which we obtain may be accurate up to 90 to 95% if you use the 3D finite element. But generally, the next method is using the reducible methods to increase the efficiency of turnaround time. These reducible structures which we use are of for the plate-like structure, which can be a Kirchhoff plate theory, Midland plate theory, or the higher order theories. These theories are based on ad hoc kinematic assumptions and which are applicable for only some type of models. So there are some other models like layer-wise theories, etc. But all these models are based on a displacement model or stress-based model or mixed method. So these are not these are based on ad hocly kinematic assumptions, which may be applicable for some problems, which may not be applicable for some other problems. So hence, to bridge this gap, the technique which has been emerging is the variational asymptotic method. So this variational asymptotic method, we can see that it is a combination of two words, mainly that is asymptotic as well as variation. So the solution which we obtain is asymptotically, the accuracy can be increased and asymptotically correct to that approximation. These solutions are obtained by using the another. In addition to the asymptotic, we use the variational method, variational calculus to obtain the solution. So hence it is coined as a name as variational asymptotic method. So it is, though it can be used very efficiently for reducible structures, it can be used for any type of problem which can be posed in obtaining the stationary point of the functional. And the another basic aspect for VAM is it should have one or more small parameters. And the results obtained from the VAM are asymptotically correct. So the overall variational asymptotic method, the procedure and how we get the final 3D elasticity solution is depicted in the form of a flow chart. And the left side is for the plate and the right side is for the beam-like structure. And the middle one shows how the VAM is applied for the reducible one. The first and foremost thing is the formulation of the potential energy of the individual layers of the composite structure. So I will be dealing with this flow chart for a composite structure, which can be a plate or which can be for a beam. So here we have to first formulate the individual layers. Why we cannot go for the total potential energy mix? Because in individual layers, there can be different materials, different thicknesses of the layers. Hence, we have to first formulate the potential energy of individual layers. When it comes to the plate, we are marching through the thickness of the plate. And when it comes to the beam, we are marching towards the cross section of the beam. So once the individual layers of the structure potential energy is formulated, then the total energy of the potential energy of the structure has to be formulated. So when the total potential energy for the plate, it will be a function of 2D strain measures, which can be the extensional strain, bending curvatures as well as twisting curvatures. And it is also a function of warpings and their derivatives. And it also will be a function of the thickness coordinate for the plate. When it comes to the beam, it will be the function of 1D strain measures, warpings and their derivatives, as well as the width and depth directions of the beam. So once this potential energy is formulated, the important step in variational asymptotic method is the identification and the estimation of the small parameters which are embedded in the potential energy. So when it comes to the plate, it can be, depending upon the type of small parameters, it can be a shell or it can be a plate-like structure. But when it comes to the beam, depending upon the type of small parameters which we are using, it can be a class R, class S, or T type of beam-like structure, where class R is called as a regular beam, S is called as a strip-like beam, and T is called as a open thin-walled shell, open thin-walled beam-like structure. Where in the R, the bending as well as the twisting curvatures are of same order, whereas in S, one of the bending curvature will be lesser order than the other bending curvatures. When it comes to the T, the twisting will be more dominant with respect to the bending. So depending upon the small parameters, the beam can be classified to this type of, mainly to these three categories. So once the order estimation has been done by identifying the small parameters, then the total potential energy of the system has to be expressed in terms of these estimated orders. So once we substitute these orders by using a bookkeeping parameter, the total potential energy will be divided into different magnitudes of potential energy. So for the first approximation, we'll be taking the first leading order terms, and that approximation is named as the zeroth order approximation. And along with this, the warpings which has been defined during the kinematic relations and thereby the strain tensor, uh, these warpings will be having the rigid body like motion. And to remove these, we will be applying the global constraints on the warping. So the total Lagrange functional will be obtained by adding the zeroth order approximation energy as well as the global constraints on the warping. So over this functional, we will be applying the calculus of variation. Thereby, we will be obtaining the characteristic equation named as the Euler-Lagrange equation, the necessary geometric as well as natural boundary conditions. So for the beam-like structure, these equations will be ODEs, that is ordinary differential equation, and for the plate-like structures, it will be PDEs. As we know that for the plate, we are going to march in the thickness direction, so only X3 is independent, whereas in beam, as we are going to march over the cross section, both X2 as well as X3, if X2 and X3 are along the width and depth direction of the beam. Hence, it becomes a partial differential equation. So once we obtain the Euler-Lagrange equation, we, along with the geometric as well as natural boundary condition, the closed form expressions of the will be okay. As we all know that ODEs are relatively easy to solve when we compare with PDEs. So wherever the PDEs, we are not getting the solution where the equations are highly complicated in terms of the coupling of the warpings. So generally we go for the expansion of the series like Taylor series, etc. And once we obtain the closed form solution abiding to the geometric and as well as natural boundary conditions satisfying the characteristic equation and meeting the 3D elasticity solution, we can take a call whether the required accuracy is obtained. If we want further refinement, perturb the warpings and make that perturbed warpings as the higher order than the order which has been estimated before that order. So once the warpings are perturbed, then the same procedure is followed, and we can do this iteration till we get to the desired accuracy. So once we feel that we are in line with the desired accuracy, then we can substitute the warpings into the total potential energy and integrate over the thickness if it is a plate, or integrate over the cross section if it is a beam. So this yields the 1D or 2D constitutive law, and by doing the 2D plate analysis for the plate-like structure or 1D beam analysis for the beam-like structure, we obtain the 2D strains and curvatures or 1D strains and curvatures as the case may be. So these are substituted into the recovery relations, which are obtained as a byproduct from the closed form solution of the warping, which yields the 3D elasticity solutions. And we have seen that for the plate-like structures as well as beam-like structure for R class or S class, up to first order approximation was good enough to obtain the accuracy up to 95 to 98%, which are as close as the 3D elasticity solution. So these are the advantages as well as the small parameters which are used in the variational asymptotic method, which has been dealt during the discussion in the first two slides. So till now, for the last 2 or 3 days, we might have, all the speakers would have discussed about the plate or a beam with a composite. So I'll be going to the another type of structure, which is a sandwich plate. The sandwich plate is a very common structure which is used in the aerospace industry. So it has mainly 3 structural parts which makes up the sandwich structure. So it has two thin, stiff as well as a strong face sheets, which are separated by a thick, weak, and strong, lighter core. So here, the construction is such that its structural behavior is similar to that of an I-beam cross section, I-beam section, where the face sheets are intended to take the bending loads that which in turn turns to be a in-plane load, and the honeycomb core is intended to take the transverse shear loads. So this is the kinematics which might have been seen in the last 2 or 3 days. The left side is the undeformed configuration. The right side is the deformed state of the same material point. If we consider the P material point, the vector can be given as the sum of the that is the sum of the projection of the point to the reference surface from the fixed point, and the vectorial sum of the reference point on the reference surface to the point of the material which we are considering. So when the loads and boundary conditions are applied, this point will be deformed to the point P star. So during that deformation, the material point will translate, rotates, as well as warp. So these are all the aspects which has to be taken care while making the position vector in the deformed as well as undeformed configuration. So to define this position vector in the deformed configuration as well as undeformed configuration, we have to use the basis. So in the these for a plate-like structure, it can be a Cartesian orthogonal coordinate system, where small b basis is used in the undeformed configuration and capital B is used in the deformed configuration. The position vector, as I discussed, it is the position vector from the any point to the point which is the projection of the material point onto the reference surface, plus the coordinate from here to the material point which we are considering. So once we define the position vector, we have to define the covariant and the contravariant base vectors. Why we require all these things? These are the requirement which will be used to obtain the 3D strain tensor. So once we obtain the covariant and base contravariant base vectors, and for a play which are given the partial derivative of the position vector with respect to its coordinate. So for the plate-like structure, it turns out to be the unit vectors along their particular direction. So in the deformed configuration, the capital B basis is used to define the position vector, and the capital B as well as the small b are related by the directional cosine matrix. And the position vector, as I told earlier, the material point and the given loads and boundary conditions, it rotates, translates, as well as warps. So all the aspects has been embedded in the position vector, and the covariant base vectors in the deformed configuration is given similar to that of the covariant base vectors defined in the undeformed configuration. So while defining the covariant base vectors in the deformed configuration, we will be introducing the 2D strains as well as the curvatures in terms of the extensional strain, the bending curvatures, as well as the twisting curvatures. So once we obtain the covariant as well as the contravariant, then we define the deformation gradient tensor, which is in the mixed form is given in the equation as given here. And once we obtain the deformation gradient tensor, we can use any type of strain tensor, whether if depending upon the type of analysis we are doing. If the rotations are small, we can use the Biot-Cauchy strain. If the rotations and the deformations are high, we can use the particular type of a strain tensor like green strain tensor, etc. So all these things we are doing because we have to make the potential energy of all the layers. So once we obtain for the Biot-Cauchy strain in the compressed format, the 3D strain vector is depicted in this slide, where epsilon is the extensional strain and kappa is the bending curvatures, and W stands for the warpings, where parallel lines shows that it is the in-plane warping, and W3 is the thickness direction warp. So once the strain tensor is formulated As we know that in a sandwich plate-like structure, we are having mainly three structural layers, that is the phase sheets, top, bottom, as well as the core. And each phase sheet can have different types of layers to form the top phase sheet or the bottom phase sheet. So as these materials are different and the thicknesses are different, we consider different warping functions in each of the phase sheet. So while defining these warpings, as I told earlier, the rigid body like motions, like is the translation motion, rotations are embedded in the formulation to remove these kinematic constraints and make the system deterministic. We have to use the global constraints on the warping. The first equation gives the translational global constraints for the warp, where I stands from 1, 2, 3, and alpha stands for the in-plane coordinates. So the first stands for the translational, as well, and the second one stands for the rotational constraints. So this is the slide which shows about the axis system which has been used to formulate the potential energy, where X3 is taken as the thickness direction of the sandwich. So this is the well-known constitutive law which relates the stress as well as the strain. And here we are talking about the 3D stress as well as 3D strain, and this is related by the stiffness matrix. So where K stands for the particular layer of for which the strain as well as the stress vector related. So once the stress as well as the strain has been formulated, we use the specific work done. We can use either the traction force on the top surface, on the upper surface or bottom surface, or the body force, which can be used. So once all this, that is the strain energy as well as the work done is estimated, we can obtain the potential energy by using the well-known formula, that is the stress into strain. And in terms of 3D strains, it is given in this way. So in the dimensional reduction process, the energy distribution in the 3D structure has to be made equivalent to that of a 2D body. So this has been, this is going to be done by using the VAM. So as I told earlier, the major aspects of the VAM is the identification as well as the estimation of orders of the small parameters. Specific to the sandwich, we are using two types of geometric small parameters. One is the ratio of thickness of the dominant in the in-plane wavelength of the plate, and other is the ratio of thickness of phase sheet to that of the core. So we have used two small parameters for the geometry, but generally for a plate-like structure, only the first one will be used. But here the core is larger than, very much larger than the phase sheet, so the second also has been used. In the physical parameters, it can be the strain, or it can be the other aspects like the ratio of in-plane to the out-of-plane stiffness of the core, and the last two has been used only for the sandwich. Otherwise, generally the first one is sufficient for the plate-like structure. So these are the orders which has been estimated, where delta here does not stand for the conical delta. It is only for this symbol purpose has been used. So as I told in the flow chart, once the orders are estimated, these orders are substituted into the potential energy. And for the first approximation, the leading order terms are considered, and this energy is taken as the pi 0. So this is the total energy. The first part is the total strain energy, and this is the second and the third part is the one which removes the rigid body-like motion, that is the translation as well as rotation, and these are multiplied by the Lagrange multipliers. So along with this, we have to use once it is formulated by using the calculus of variation, we obtain the Euler-Lagrange equations and natural boundary conditions. And one of the important aspects of the 3D solution when for a composite beam is that it has to satisfy the interfacial continuity condition. These are of two types. One is the displacement continuity and other is the stress equilibria at each of the interfaces. So this for the sandwich, as we have discussed earlier, it has to be satisfied at this position as well as at this position, where the face sheet is getting connected to the core at the top and the face sheet connecting to the bottom of the core. So once we obtain the closed form solution for the warping, we can decide whether we have to march to the next approximation. If we want to go for the next approximation, which is generally better to go for it to get the good accuracy, at least we have to go up to first order approximation. So here the zeroth order warpings has to be perturbed, and the perturbed warping orders will be greater than, order-wise it is greater than the orders which has been used for the zeroth order warping. So the procedure which has been, the procedure for the first order will be very much identical to the zeroth order approximation. So even the solution is also identical to that of the zeroth order approximation. So once the warping solutions are obtained, this is substituted into the potential energy, and integration of this potential energy with respect to the 2D strains and curvatures we will be obtaining the normal force as well as moment resultants and the transverse stress resultants. So the second derivative of the potential energy with respect to the 2D strains and curvatures, we obtain the well-known ABBD matrix, which is the laminate stiffness matrix that relates the 2D strains as well as the 2D force resultants. And this is the base model which will be used for carrying out the 2D analysis. So the 2D analysis, what we'll be looking from the 2D analysis is the 2D displacements, the extensional strains and their derivatives, the bending curvatures and their derivatives, and the transverse shear strains and their derivatives. So these are all the outputs which we'll be looking from the 2D plate analysis. So once we do the 2D plate analysis, we'll be having all these informations at all the locations of the coordinate. So as we discussed in the flow chart, one of the important aspect of the VAM is obtaining the 3D responses of the structure. So these 3D responses can be divided into displacements, the strain, as well as the stress tensor. The 3D displacement is nothing but the difference of the position vector in the deformed configuration to that of the undeformed configuration. And for the plate-like structure in the compact form, it is written here, where small u is the 2D displacements. And we know that we have estimated the warping. Substituting the warpings into the 3D strain tensor, we obtain the 3D strain tensors. Then using the constitutive relation, we can obtain the 3D stress. So the overall sandwich plate-like analysis in the form of a flow chart is given in this slide. So the present formulation has been validated with elasticity solutions as well as 3D finite elements. That is especially with the Piago solutions. We have compared this 3D elasticity solution, and for the 3D finite element analysis also has been carried out with the 3D finite elements, and the results from the VAM has been compared with that. So for this analysis, we have taken the top and bottom phase sheet as a bidirectional composite with 43090 as the fiber and M18 as a resin. So we have considered a plate of that is the top phase sheet of 1 meter by 1 meter having 0.5 mm thickness, and the core as 1 meter by 1 meter and 50 mm as the thickness, and the honeycomb core nomenclature is given here, where CR stands for the corrosion resistant grade 3, and 3 by 16 is the cell size of the core in inches, and 5056 is the aluminum alloy, and 0.0015 is the thickness of the foil of the core, and the last one stands for the density of the core in pounds. So the material properties used for the analysis are shown here, the phase sheet as well as the core. So these are the stresses, the in-plane stresses of the plate, or the in-plane responses of the plate in terms of the stresses for a uniform pressure of around 1000 newtons per meter square. So where we know that the core should not take the bending load, so hence the stress in the core is 0, and the phase sheet should take the bending loads, and you can see that the phase sheets are taking the bending loads, and this is the 0 stress in the core. Both the in-plane sigma 11, sigma 22, as well as the in-plane shear stress. And the red line shows the stress distribution obtained from the 3D finite elements using the Nastran solver, and the dotted line shows the results obtained from the VAM. So as we know that for the transverse shear stresses, there should be the continuity of the stress at the interface, where we can see the continuity of the stress at the interface when we have used the 3D finite elements as well as from the VAM. And even we can see that the stress boundary conditions are getting satisfied at the top and bottom surfaces of the sandwich for the transverse shear, as we didn't apply any transverse shear loads. And for the normal load, where we have applied around 1000 newtons per meter square, so where we can see that the boundary conditions are satisfied. That is, we applied on the top of the top phase sheet, and at the bottom of the bottom phase sheet, no load is applied, and hence it is 0. And you can see that stress continuity at the interfaces of the core and the phase sheet. As the stresses are continuous at the interfaces, the strains are discontinuous, which we can see, and it is in line with the results from the Nastran. So these are the 3D displacements which has been obtained. We can see the continuity of the displacements at the interfaces. So this completes about the reduction of the 2D like structures or plate like structure. The last part is the beam like that is VAM applicable for the beam like structure, which will be dealt by my friend Mr. Jebin Thomas.
Everyone. So this second part would be not in detail about what beam analysis itself. It's just that we, we'll be addressing some of the pain points where students of VAM commonly have, and I'm trying to demystify the theory of VAM as much as possible, using a much more basic level of explanation. So here you can see a very similar slides that you've seen before, but the only essence that you should be focusing on is how do you make sense of it. So this is from the undeformed to deformed state. It would be separating it into a rigid body displacement and the rotation of the deformed, and as well as, and finally the deformations that would take place. So in the first two cases, it would be exact as it is. It's only in the deformations themselves where any of the approximations that would come, depending on the type of strains that you're trying, if it's a linear or quadratic case. And then this is a very harmless looking term, which can come much problematic, which I would be addressing in the future. So this is more required when you're trying to finally, once you're done with the dimensional reduction, you have to get back the results in 3D. And this, it's a common question as to how many 1D strain terms are required. So it depends on your use case. As if you want to incorporate gamma 1.2 and gamma 1.3 shear terms, you are free to. But thing is, it doesn't matter. So the information is contained during the dimensional reduction. It's just that the change of basis would just be the factor to consider. So that would be the difference between a big V basis versus a big T basis seen in the image. So when you say the 4 strain terms, the term generally used to note them would be generalized 1D strain term as opposed to just 1D strain terms. And then the difference would just be reflected in the warping solution themselves to go with the 4 terms versus the 6 terms. So that would be incorporated. And then this is where the point where most students do not pay enough attention as to classify the problem according to the small parameters. So you have to be very careful as to identify what kind of structure are you analyzing. So here, generally there are class R, S, and T. So depending on what strain measures would be dominant, if all strain or deformations are of the same order, you can consider a regular class. If one bending is dominant, you can consider a strut-based or an open section where torsion dominates. So again, the choice of small parameters will actually make or break your solution. So you have to be very careful as to what terms are you going to consider or reject. And this is again very similar to how shell analysis is also done, where what all constraints are generally considered. So this is how a warping function should look like. So just to show how it actually, it's actually function of 2 and 3. That's a 2D representation of what it looks like, a small rotation. And then the second and third set of equations are just the moments about the warpings themselves. And the angular brackets are just to average out across the cross section. And then the most time-consuming part of the whole process would be solving the GDs themselves. So since 2 variables are usually involved, it often does not lead to a closed form solution. Sometimes you might be lucky, most of the times you won't be. So again, depending on the class, you can make certain ingenious innovations. So in case of classes, I think you can refer to Professor Dinish's thesis itself, where he has further split it into 2 separate ODs. So which was more conducive to get a closed form solution. But in other cases, you will have to settle for a Taylor series expansion and then try to fit the solution while trying to reduce the residual that's involved. And then again, when you have a Taylor series, then you might have more number of equations to satisfy. You might have less. So it's about what all conditions are you going to prioritize. Sometimes it would be the Euler-Lagrange themselves, might be the warping continuity, might be the interface conditions, might be the shear condition. So it is depending on the problem itself that you have to focus what has to solve first and then try to fit into the remaining ones. And this is just an indication of how does a GD look like for a very simple class R cross section. And then in a very simple way, you can generate out what the 0th order constitutive law looks like. It is very similar to a classical solution. So here, there won't be any, this is without any initial curvatures or twisting considered. And then if you are considering initial curvatures and twists, there will be off diagonal terms that are more, significant depending on the type of structure that's been solved. So this is where you should be also mindful as to, so I will just go through last 2 sections of focusing on certain preliminaries that are missed by many. So I thought I would just address it in a more intuitive sense, just to get what exactly is a Lagrangian and what are multipliers used for. So our problem is essentially solving a functional to maximize or minimize it, right? So for us, it's a strain energy functional. So that means we have to minimize it. So, and it is subject to constraint, which for our case, it would be warpings. So F would be in this case. So I'm just describing a very simple 2D plane. So there are only 2 unknowns in this case. And if this is the function to be maximized or minimized, and G is the function that is a constraint, you can pose a Lagrangian in terms of this form, F minus lambda G, where lambda is the Lagrange multiplier. So which means if you are taking a variation of Lagrangian equal to 0, that means all 3 what do you call components or the partial derivatives would also be 0. So what does that mean when you look at the image itself? So you are seeing that the variations of both are somehow equal and just differs only by a scalar quantity. So that is what's happening at the limit point. So it's essentially the same direction. It's just it's flipped, and the ratio between the red arrow and the blue arrow is actually what the Lagrange multiplier is. So that's just to get an intuitive sense. So this then can be what you call scaled up if you have n number of unknowns as well as m number of constraints, and just that it would just scale up accordingly. So that is how you have to try to visualize the problem and somehow try to get a sense of are you getting near to the solution or not. And then this is the small topic of 3D rotations. So this is used quite extensively in our daily lives as well, in addition to aerospace, also even in our mobile phones, just to calculate the unique rotation of a point in space. So Euler himself had established that you need at least 4 parameters to have a singularity expression of how to place a 3D rotation in space. So the first 3 would be to place the axis itself or the vector in the 3D space, and the other would be the rotation around. So in the first, you can have this. So this was the relation that was derived by Euler himself, and then it was expressed in terms of half angles as well. But Rodriguez parameters is something where we are using an additional constraint, because the big B system, there is the which is the deformed configuration, is an orthonormal system. So you can use such a condition to eliminate one and just use 3 measures. It's only the side issue is that it won't be singularity free. It will be singular. Singularity issue will come at alpha equal to 180 degrees. So this last expression is usually used when you are trying to extract back the 3D rotations. So here theta is actually the twist and the curvatures are coming, curvatures along the second and third axis. So which will be useful when you are first finally done with the cross-section analysis, and you also do the 1D nonlinear analysis. And then the last slide, I would like to just give you an intuitive sense of what an exponential mapping, as well as a very harmless another character called SO3, which is a special orthogonal group. So this is a set of all 3D rotation tensors. So this comes under differential geometry topic, which is something I would not recommend going in depth into, but it is useful to get an intuitive sense just so that you understand what the rotation matrix actually is. So you actually use, in the previous, I think I had shown that CBB was shown earlier in the shell explanation that BI dot BJ, so capital BI dot small bj, would actually give you the rotation. So if you have a finite rotation and small e is the unit vector, you can have an exponential expression of the P hat itself. So P tilde is actually the antisymmetric matrix. So what is the use of an antisymmetric matrix? Is that it actually, if you have a unit vector at I, the tangent space to this particular manifold would be on the would be termed as the antisymmetric matrix. That is somehow magic, but there is a proof to that. And once you are on that Euclidean plane, then you try to bring it back towards the manifold. So that is where this approximation, when you're trying to express in terms of Taylor expansion. So as n approaches infinity, it actually comes in as e raised to a, which is the exponential map. So this is where most of the director vector theories like Koszary shell, which is also geometrically exact shell theory, which is a very favorite word of our lab. So that also comes in from there. So this is where I would stop at. So it's always useful to have an intuitive sense so that makes all of the solution process much easier, and you are not lost while you are encountered with more tedious looking solutions. So I would stop by saying that this should be a start of what you call more engagement with the former lab members as well. So we all have collective work that has been done before, rather than just focus on the results. It's always better to build a good foundation, because sometimes it takes some time to digest what has been done. We are truly sitting on the shoulders of giants, like Professor Dinesh as well as Professor Hodges, and just himself. We are feeling more what do you call adventurous. You can explore Professor Wojciechowski's books as well. You get the true sense of where it all comes from. So I would stop it at that. So thank the organizing team and Professor who was present this. So I hope this enables more students to keep asking more questions. We might not always have the answers, but at least we would try to nudge you in the right direction. So I will stop it. Great. Some questions, both Professor Mr. Peereswara.
Before we get to the questions, I should say that if at all out of the 24 talks in this workshop, we have something as a takeaway message, especially for those of us who are not exposed to VAM, and also those who are working on VAM but are finding stumbling blocks. This is the talk. Because actually Peereswara was hesitating whether, since there are so many talks already, should we give it or not? Would it be too much of a crowd into the whole thing? But I thought it was kind of essential. We were also trying to see where to fit it, because giving it right at the beginning would have been one of the ways of looking at it. But to do it on the last day was also another way of doing it. Because these two gentlemen have a unique standpoint from which we can understand VAM, because as the introduction already was said, Peereswara is one of the senior most scientists in the Indian Space Research Organization, which is world renowned for its wonderful activities. And he's been involved with some of the leading space programs, as already pointed out, be it Chandrayaan, Mangalyaan, or Gaganyaan. For somebody who is into the industry like that and who works on typical industrial problems, to understand what is perceived by the general public as a mathematics-oriented thing, which is very rigorous and which is very difficult to understand, the learning curve is steep. Many of these things are true, but it is possible, is something that has been demonstrated by him. He's done it for plates, sandwich, as he pointed out. He's worked with Jebin's team, leading it from the front in terms of the beam problem. So he is somebody who has an industrial background, but an overall perspective of VAM, applying it to many different cases. And so I thought coming from him, it will be really nice. And also, some of my previous courses on VAM, I've had him speak for 2 or 3 hours on the plate or shell models, where I'm mostly talking about the beam models to draw in a parallel. And a lot of the things that he conveys there has been very useful for the students as well. And Jebin comes from an entirely different angle. Very few people have both the depth and the breadth as far as VAM is concerned. And he has a humongous experience in terms of working on VAM-related problems. And he has a passion for it. It's not that it's kind of imposed on him and he's working on it. So he really tends to take, and you would have seen the way he has designed these slides. I've not seen these slides before, so he has done it quite recently. And he has put in a lot of effort to see from where he was and where he has come. What are the stumbling blocks he faced, and which could be common stumbling blocks for many other students? And he's tried to bring that into perspectives. They might seem like disconnected nuggets, but many of you who have already started working on VAM and are somewhere midway through will see, if you have not already, where many of these intuitive perspectives fit in. And I think that's very, very important, that we don't get lost in the details of the mathematics and lose the bigger picture. Every now and then you have to go up to the 30,000 feet altitude and see the bigger picture, where your work is and where it fits in, and then only you come back and go further in the depth of your research. So that really helps you set things in perspective every now and then. And it was very nice of him to offer also the possibility of you interacting with him and the senior students and lab mates in general. I don't want to use the former because if Srikanth is listening or anybody like him is listening, they might consider it as an offense. But but the fact remains that we are a very close family, and I think it's very important to utilize the so-called elders' knowledge and wisdom, practical especially, in terms of advancing your own works. I'm sure it will benefit not only in a much refining, but also in speeding up your works as well. So thanks once again to Jebin and to Peereswara for agreeing to give this talk. I know we are already into lunch, but this is an important talk where especially I think the students can benefit a lot. Of course, many of you can have interactions beyond this as well, much longer discussions. But any important points, I think there are quite a few people waiting online as well. But first, we'll throw it open to the audience, live audience here in the hall. Maybe we should first take it from the guests.
No, this is so I'm not exposed to one of the persons that he mentioned, not exposed to one. So I see the complexity, I see the advantage. So after 3 days, 3 days and after, I really learn a lot on from the previous presentation, from this one. So learn and so a little bit more about your work now. But so I cannot get yet all the details. But a curiosity that it came, because you have a beam, you have a plate, will you have a shell? Because this
Yes.
3D location reminds.
Yeah, it is a plate is just a what is called a subset of this.
Yeah.
So in Kosarat-based theories, they use unidirectors, which is independent of the others, while as FEM does a very degenerate shell where everything else is in terms of the in-plane terms, right? So here, in terms of when I speak in terms of VAM, initial curvatures are where it's captured. It's just that you just need to be mindful of what all are the variables, in what form are they appearing, and you have to identify the common things. So this was one of the common things I had noticed while I was exploring Kosarat shell, which was the exponential mapping and the Rodriguez parameters that I use.
So we already have a VAM-based shell theory.
Okay.
It's just that it was not presented.
Okay.
The whole idea has been to demystify. This is just to demystify the whole process of VAM itself, rather than just get afraid by the length of the solutions. You just need to be able to track and find the patterns as to where it's recurring. Computers will do the rest.
So you use this.
Yeah, that's what they.
And so the next step will be to join the sandwich plate with the shell and doing a sandwich and shell for space application, or no?
No, this so just what do you call it? The whole team was made just to show an example in one case,
Yeah.
while being true to the essence rather than just to get lost in the ends.
That was the. Okay.
Students, any quick questions?
I think the questions might follow
Follow.
Yeah.
after the talk, which is the whole point of the presentation. It's intended to be a start of a list of conversations. For a couple of I already have had initiated. So this was based on some of the pain points that I found in common while I was discussing with them. leads to more thoughtful conversations.
Anybody on the online audience? Anything you'd like to say or ask?
Yes, this is Ramesh here. Actually, after summarizing by Professor Dinesh, I think nothing is much left out to say. But I thought I should thank these two guys who had made very good, interesting presentation. And also the way it has been made such a way that many people are very hesitant or many people are finding difficult to understand the terminology. So this kind of way they made a presentation, it will definitely will be useful for all the community and the people who are going to use in future. It will be very useful. So I can say only because it is a voluntary work by Jebin. So I can only request him saying that you can extend some more other topics maybe and make sure it will be available as a video recordings for next generations so that it will be so
There are many other ways,
and
like you can have a private repository of codes and presentations, even using GitHub tools like that. So there are many other avenues other than just just the videos and having intermittent what do you call presentations. So that is also something the whole community can make use of. So
oh,
this is a
sure.
collaborative effort, so which is where you can avoid reinventing the wheel as much as possible, and then focus on the actual problem at hand.
Yeah, yeah, that is true. That is true. Thanks a lot, Peereswara and Jebin.
Thank
There's also the book with the compilation of the emails. As I said,